A very warm welcome to this demonstration session for demonstrating the continuous time systems and their properties. In this session, we will see an example of a system and verify the two properties that we have learned regarding the continuous time system. These properties include the additivity and the homogeneity. So let us first check for the system 1 that is written on the screen, which is represented in the functional form as y of t is x of t squared. Now the examples here have been chosen such that the combination of the linearity property and the time invariance property is well studied. So in this first system, as seen in the previous lectures, we know this system is nonlinear. Let us check or let us prove by means of this simulation experiment that this system is indeed a nonlinear one. So we have shown that a system is linear if and only if it satisfies the two properties, which are additivity and homogeneity. So to show that a system is nonlinear is to disprove any one of these properties. So let us take an input of x1, which is the sine of some frequency, and x2 to be the second signal of the same frequency, but now it is cosine. Now we apply the sine and the cosine separately to the system. This leads to the outputs corresponding y1 and y2, which now is the square of the corresponding sine and the cosine. Note that in the MATLAB notation, we need to take the pointwise square, and that is why the notation over here represents a dot and an exponential. Now the sum of the corresponding outputs is y1 plus y2, which is represented by y. Now the output corresponding to the sum of the inputs is given by x1 plus x2, which is pointwise squared. Now we are going to verify whether the sum of the outputs y is the same as the output corresponding to the sum of the inputs, which is actually the property of additivity. Let us plot the various inputs and outputs and verify the property of additivity now. So let me run this code or this section of code to illustrate the result. So we have obtained a plot of the input versus the various outputs. So the plot on the first row represents the two inputs that we have applied to the system, x1 and x2. So the first graph over here represents the sine, which has a frequency of 5 Hz. The second graph over here represents a cosine of frequency 5 Hz again. So there is only a difference in the phase. So if I shift the first signal by a phase angle of 90, I get the second input. Now the corresponding output of x1 is represented by y1, which is now a square of the sine wave. So if I square the sine wave, what I get is a waveform which has only positive values, which takes only positive values in the interval 0 to 1, which is the interval of interest to us. Similarly, on squaring the x2, I get the output y2, which is now the square of the cosine waveform. Now coming to the third row of the graph, we have the sum of the outputs y1 plus y2, which is represented by the straight line here. It is the straight line because we know that the sum of the squares of sine and cos would result in the value 1. That is, sine squared theta plus cos squared theta for all values of theta has the value 1. Now, the plot in red is what is the output corresponding to the sum of the inputs, which is x1 plus x2 whole square. Now, it is clearly seen that the sum of the outputs is not the same as the output of the sum of the input. So this easily disproves the property of additivity for the system, and hence this system y of t equal to x of t squared is non-linear. Now let us check for the time invariance property of this particular system. From our previous discussion, it is clear that this system is time invariant. We shall check this with the help of the example x equal to sine of some frequency. So as earlier, we take x1 as the input now, which is sine with a frequency of 5 Hz. Now the output is the pointwise square of the input x1, which I represent by y1. Now I shift the input, which is now represented as the x shift. So to shift a signal, what I do is I introduce the 0 as the value as many as the shift. In this particular case, we are shifting the signal by an amount of half a second. In the interval 0 to 1, I should add half the number of zeros. So the obtained signal which is shifted, the input shifted signal, can now be represented as an initial set of zeros, and then the sine signal appears at t equal to half. Now let us plot these signals and their corresponding outputs. So what is represented here in 3 rows of graph are: the first row represents the actual signal, which is represented by the dotted blue plot, x of t, which is given as the sine wave input of frequency 5 Hz. Now x of t minus half is the shifted sine wave. Now you can clearly see that the value of this sine wave is 0 till a time of half a second. The corresponding outputs are represented in the same color in the second graph. So you can see the square of the sine wave, the actual input, is the blue dotted line here. Clearly there is a doubling of the frequency, which you can observe easily. Now the output corresponding to the shifted input is shown in the pink graph, which is still 0. The output is still 0 up to the time of half a second. The third graph corresponds to the output being shifted by the same time of half. So you can see that y of t minus half, which is obtained from the blue graph in the second row, on shifting it by half a second. You can see that these two graphs, the pink one in the second row and the blue one in the third row, are coinciding. Now this is not only true for the signal sine wave that we have considered, but it is also true for any signal that we consider. It can be easily shown analytically that this system y of t equal to x of t squared is a time invariant system. That brings us to the end of this demonstration. Before we conclude, let me discuss what are the properties of the other 3 systems in this page. So the other three systems, the system number 2 is represented by y of t equals t times x of t. It was discussed that this system is linear because if I supply the sum of the inputs, the output that I get is the sum of the corresponding outputs. But the system is not time invariant. It varies with time, so this is a time varying system. So that is a system of second kind. It is linear, but it is time varying. The first system is non-linear but time invariant. Now system number 3, y of t is x of t squared. X of t squared, t is the variable that is squared. It is clearly seen that this system is linear and it is also time varying. Time varying because here we have t squared, which means that there is some dependence on the time. Now the last system over here is both linear and time invariant because it is just a moving average with two samples that are taken. It can be easily verified that the additivity and homogeneity property, which composes the linearity property, is satisfied here, as well as the time invariance property is satisfied. So let us come to an end of this demonstration by taking these two interpretations of linearity and time invariance. Thank you.